Uh, so H is a field conjugate to P. If I consider P as an order parameter, and there is an energy F, H so F is a functional of P, which in general is known, and I take the functional derivative, and that gives me the orientational field that I call H. Now, if I work in 2 dimensions, and in most of what I will show you, it will be in 2 dimensions, P is a unit vector, so P is cosine theta. And H has 2 components. One is perpendicular to P. That will give you the torque that tends to make P uniform. And the other one is along P. This one is not very relevant because it's kind of a Lagrange multiplier to impose that the modulus of P is 1. So I won't talk about this one. It shows up in the equations, but it's not very interesting. Now, if you have a director which is cosine theta, sine theta, the only thing I care about is H perpendicular. And H perpendicular, what I will choose is something like K radian squared theta. So K is a stiffness. For the people among you who are familiar with liquid crystals, it's called a Franck constant. In 2 dimensions, there are 2 Franck constants, and I'm assuming here that they are equal. It doesn't change very much if they're not equal. You can still do it. So this is one of the forces. I need a conjugate force, a conjugate flux to H. This conjugate flux is essentially the rate of change of the polarization P, or of the director P. So I'll call that big P. dP dt. In fact, if I want my theory to be invariant by translations and rotation, I have to take the co-rotational derivative. So for a vector, it's easy to write. So I'll write it plus v dot grad t. This is the thing that ensures that your theory is invariant by Galilean transformations. And then I want it to be invariant by rotation, so plus omega cross p, where omega is the local rotation, and the local rotation is 1/2 of the vorticity, so it's 1/2 of the curl of the velocity. So that's the force. This is the flux conjugate to the force. Now there is a force which is hydrodynamic force which is associated to momentum conservation. This is the velocity gradient. And what I want to do is I want to make this traceless, because if you have an incompressible system, for an incompressible system, it won't change many things. It won't change anything at all. So I will subtract from that 1 over d. It's plus, I agree. 1 over d gamma delta alpha beta. Now the flux conjugate to the velocity gradient is the mechanical stress, and so I will call it sigma alpha beta tilde. But I have to explain you what this stress is. So if I have a system which is pneumatic, I'll call sigma total alpha beta the stress. Now there is one component of the stress that you know, which is the isotropic component of the stress. It's 1/3 of the trace. That's the pressure. So I will subtract the pressure. So this is minus P delta alpha beta. That's the diagonal part of the stress. Now, if I have an orientation, if I have a pneumatic system, the stress is not symmetric. If you remember your first course on hydrodynamics, they told you the stress is symmetric because there is no torque. But that's only true if the system has no preferred orientation, so if it's invariant by rotation. If the system is not invariant by rotation, the argument that you are given at this place does not work because there is a preferred orientation. The fact that the stress is not symmetric means that there are torque, and torques is an anti-symmetric component of the stress. So I won't talk about it very much, but there is a term sigma anti-symmetric alpha beta. That means if I change alpha and beta, this is changed in minus sigma alpha beta. This is known, and it turns out that for the theory that I'm doing, it's only passive, which means there is no active component to this stress, so I can take the result that people use when they work on liquid crystals. If I had not a pneumatic, but a system which is chiral, then I would have to worry about that, and there's an active part if the system is chiral to this anti-symmetric component of the stress. The part which is left is what's called, so I took the whole anti-symmetric part here, took out the trace, so I have a traceless tensor, this is why I put a tilde, and it's symmetric because I took out the anti-symmetric part. So that's called the deviatoric stress in good hydrodynamic books. And this one is the flux which is conjugate to the force. Now, if we are an aficionado of liquid crystal, there is something which is called the Ericsson stress, which is a static stress. If I want to be exact, I have to replace this term by the Ericsson stress. However, if I'm close to equilibrium, the pressure and the Ericsson stress are the same. Believe me, I checked that many times. It becomes pretty painful to derive if you want to put that, but that's how I should define the flux. So the force is here, the flux is here. So that's the same as for a liquid crystal. Then I want to take into account the fact that the system is active. And the strategy that we use from the first day is, you know, all kind of things on how the system is active. It's because there are cells and the cells have nutrients. Of course, you don't want to go into that. So the thing that we decided is that the system is active because it consumes ATP. It consumes ATP because you give nutrients, but it consumes ATP and there's a chemical reaction. ATP is hydrolyzed into ADP, and that provides the energy for most biophysical systems. So when one ATP molecule, it consumes into one ADP molecules, you get energy. You get an energy that I call delta mu. This is the energy that you get when you hydrolyze one ATP molecule. And I'll call that delta mu. Typically in a cell it's 25 kT. So it's not the energy, it's the free energy, which means it depends on the concentration of ATP and of ADP and of phosphate. And there are a few experiments where people try to change that by changing the concentrations. Now are there chemists in here? No? This is the delta G0 of the hydrolysis reaction. I learned that. It's the difference of chemical potentials between ATP and ADP. So that's the variable that will control the fact that the system is out of equilibrium. If the hydrolysis reaction of ATP is at equilibrium, this is 0, then the system is not active, and that's not what I want. So this is non-zero, and there is a flux that I call small r, with no arrow on top of it, and this is the rate of consumption of ATP. what I call the rate of consumption of ATP. It's the number of molecules of ATP which are hydrolyzed per unit time and unit volume. And then what Ondager tells you is what you have to do is you take these three fluxes which are here. So I have one vector, one tensor, and one scalar. And you write that there are linear functions of these three forces which are here. And what you should do is write the most general linear relation, so the most general transport matrix, I like to call it, that respects the symmetry of the problem. And the symmetry of the problem is the fact that my system is pneumatic. And you have also to pay attention to what happens when you reverse time, because some of the terms dissipate energy and some of the terms don't dissipate energy. So I won't do that, and you can do it explicitly. What I will do is write you what you obtain at the end of the day. So I obtain three equations, which of course I don't know by heart. So sigma, tilde, alpha, beta. In the derivatives, which are only co-rotational derivatives. Oh. So I assume, no, merci. I assume that there is conservation of momentum, so there is no transfer of momentum to the substrate. In this case, momentum is conserved. If the tissue is on top of the substrate, momentum is not conserved, and the divergence of the stress is on zero. So the divergence of the stress is equal to the friction force. So there you have two strategies. Either you forget about the fact that momentum is conserved, and you write equations for active system with non-conserved momentum, which is what Hugues was writing, for instance. Or you say everywhere except at the surface, momentum is conserved, and I write a boundary condition. And the boundary condition itself could be active, which means it can be friction, but it can also inject energy into the system from the surface, which happens for tissues. So sigma alpha beta, where is it's here. So it's 2 eta v tilde alpha beta, where this is this, where I subtract the trace, plus nu1 p alpha h beta plus p beta h alpha minus 2/3 over d. D is 3 in 3 dimensions, it needs 2 in 2 dimensions, p gamma h gamma minus so in the stress I have a term which is a viscosity. Now for the people who know about liquid crystals, there are 3 viscosities for an incompressible liquid crystal. As I don't want to write 3 viscosities, I only write 1. Doesn't matter very much because couplings like this one will make the effective viscosity anisotropic anyway. So if I consider them as phenomenological constant, I will get the anisotropy of the viscosity in the end. But I should write 3 viscosities instead of 1, because that's a viscous term. That's a coupling between the stress and the order parameter. If the order parameter is not homogeneous, H, which is here, is non-zero, and there is a stress associated to that. And that's a stress which is active, on which I will come back afterwards. Then I have this vector here, P alpha. So it's H alpha over gamma, gamma 1, minus nu1 p beta alpha beta. So there is a term which tells you how the rate changes because the orientation is not homogeneous and there is a field and there is a coupling to the velocity gradient. I don't put an active term here. Believe me, I can insert it into here, so the active term that I will get from here doesn't change the physics at all. And then I have an equation for R, which is lambda delta mu So these are what I will call the constitutive equations for the active system. If I want to study the active system, I have to write these constitutive equations, and I have to write the conservation laws. So what I will write is this plus conservation law. So the advantage of writing it like this is that any term which is active is proportional to delta mu. If I am at equilibrium, delta mu is equal to 0. So the terms that disappear are this one and this one. Now this one is kind of trivial, because if there is no flow, you inject energy into your system, and if there is no flow, you inject energy at a rate which is lambda delta mu. So that's what this term is telling you. It has to be there. You know that there is energy injection into the system. That's what basically, I mean, fundamentally makes the system active. The only other term which is not passive is this one. And that's the one I will comment. Before I do that, I don't know how much you're familiar with the physics of liquid crystals. This term here, gamma, is what's called the rotational viscosity. So if the orientation is not homogeneous, there's a finite field, and because of this finite field, there is a rate of change of the orientation. This coefficient gamma is homogeneous to a viscosity, and it has to be positive. So it's a viscosity which is associated to the rotation of the orientation. Oh yeah, I said it last time. Yes, I want to. I'll come back to that. Who is... Attends, il y a une question là-bas. T'es trop grand, toi. Sorry, say that again. Yes. So I'm coming to that in a second as well. I will show you that.
So the reason why you don't have delta mu in P alpha is because
I didn't try. No, because it will be a term which is P alpha times some constants times delta mu, but that's like a field which is here. So my H will be the total field, including the pneumatic field, and then there will be the cross term here. So the next one I want to comment, so this is the rotational viscosity. The next one I want to comment is this one. So this one is easy to understand. I will make a small drawing. Suppose I take a liquid crystal, a pneumatic liquid crystal. By the way, this is how your watches that have liquid crystal display work. I put the liquid crystal in between two surfaces, so the molecules are like this, and then I shear it. Now if I shear, I tilt the molecules. They will turn like this at an angle theta. And believe me, or make it as an exercise, cosine 2 theta is 1 over nu. Now some of you, all of you, will immediately notice that there is a problem if nu is smaller than 1 in absolute value. If nu is smaller than 1, if you do this experiment, there is no steady state, and the orientation just tumbles. So I will assume that nu is larger than 1. For some problems, like the one I will talk about just afterward, it doesn't matter very much. So this is called nu is called the flow alignment parameter. You put a flow and you get an alignment of the liquid crystal which is tilted. So I discussed that. Let me, before I discuss that, come back to, yes? Here? No. No, because this is a cross term between R, between this one and V alpha beta, so it's a cross term between these two equations. So there's no delta mu here. Let me come back to the question that he asked. I said that I will work close to equilibrium. So close to equilibrium, you know that there are things which are called Onsager reciprocal relations. Now, what this relation tells you is that if you have a term in here which dissipates energy, the cross terms should be equal. If you have terms that are reactive, which means which don't participate to the dissipation of energy, then the term should be opposite. Like this new one term is a term that don't participate to the dissipation of energy. There is a plus sign here, and there is a minus sign here. The active stress has a minus sign here, and it has a plus sign here. So it's a reactive term. If I write the energy balance, I shouldn't write it explicitly because in the end it disappears. The other thing last thing I want to say is that in practice, I have the choice of what I want to call fluxes and what I want to call forces. I could replace a flux by a force and redo the whole thing. Of course, I would get different coefficients, but it's the same thing. And it's well known in liquid crystal hydrodynamics. If you take the book, I'm sorry, I'm a great fan of De Gennes, so you take De Gennes' book, and it gives you the two ways to do it. There is one way where you consider what I did, which is the force is the velocity gradient, and the flux is the stress. This is the American way of doing things. And there is a way, which was the French way in the beginning, where here you put the stress, and here you put the velocity gradient. First time I showed these equations to De Gennes, he told me, but you did it the wrong way. I prefer the other way. I said, too bad. And you can check, one of our postdocs, Abid Bassou, checked explicitly that you can map one to the other one for these active systems. So the last thing I want to talk about is the active stress. So this is this term here. It's a stress. Now, as Ramin was saying, it's proportional to the pneumatic order parameter, so Q alpha beta, which is P alpha minus 1/3 delta alpha beta. The thing that I want to insist on is that this is not a pressure. It's not proportional to delta alpha beta. It's kind of a normal stress difference. If you're in 2 dimensions, it will contract the system in one direction and dilate it into the other direction. Now this is kind of a projector along P, so it's obvious that one of the eigenvectors is P, and in 3 dimensions the 2 other ones are 2 vectors perpendicular to P. Now depending on the sign of this coefficient zeta, you will contract along P and dilate in the perpendicular direction. That's what happens when zeta is negative. So that contracts along P. And that dilates in the perpendicular direction. So I will call that a contractile stress. Most of what I will show you will be for contractile system. You can tell me that I could have changed the sign, but I'm lazy, so I wrote it like this the first day, and I haven't changed since then. So I don't want to change, otherwise I will mess it up every 2 seconds. Yes? Oh, no, here this is something, it has to be symmetric in alpha and beta, so this term makes it symmetric, okay? And it has to be traceless. Okay, so this is, and this term essentially doesn't play any role, this diagonal term, okay? So that's what I want to use, as I said. There are systems So in what I will show you for the tissues I will show you, zeta is negative and it's contractile. And again, when I call contractile, it contracts along the director. There are systems or even tissues where zeta is positive. In the systems that Hugues showed you with microtubules, zeta is positive and the system is extensile and not contractile. So that's what happens when zeta. Okay? So that's what I will use. I will give you 1.5 example on how I can use that. What I want to discuss is what I will call the Frederick's transition. So that's my number 2 here, or the spontaneous flow transition. So let me start to have my problems with that. Let me show you the systems that I want to study. I want to study a very thin film of active gel. So this is a solid substrate. Then I put a layer of active gel with a thickness L here. And what I call active gel is something that satisfies these equations. And I don't do anything else. Now, what I'm claiming is that if this is thick enough, it spontaneously flows, even if there is no pressure gradient. Now, let me first tell you why qualitatively it does that, and then I'll do it semi-quantitatively with kind of hand-waving arguments, because otherwise I will have to embark in very messy calculations with that, and it will take me 2 hours, which I certainly don't want to do. So I will assume that close to the two surfaces, I will put it like this, the orientation is parallel to the surfaces. You can take it parallel, you can take it at pi over 2, 90 degrees, it's about the same thing. Now, believe me, but it's almost obvious, there is one obvious solution to this problem, which is everybody parallel. So everywhere P is like this. That satisfies this equation. I will assume that there is no velocity field, so V alpha beta equals 0. There is no derivative here. This is 0, H is 0, because the second derivative is 0. The only stress that will remain is this one. This is a constant stress, so it gives 0 in the force balance equation. And the other thing which is left is that I inject energy into the system, and I inject energy between these two. So that's an obvious solution. Now, and I wouldn't bother you with that if this was the end of the game. Now, what I want to do is look at the stability of this solution. In order to do that, I will assume that there is a perturbation in the system, or a fluctuation, whatever you want, that P is parallel on the surfaces, but in the middle is slightly tilted. Now, you will agree with me that if this is true, there is a gradient of P, because P is like this, and here it changes. But if there is a gradient of P, there is a gradient of active stress. Now, if I write the force balance equation, that the divergence of the stress is equal to 0, the term coming from here is non-zero. And the only way you can balance it is by this term here. So any active system whereby any chance I create a gradient of active stress, I generate flow because I need in the force balance equation to have a stress that balances the active stress. So the one that will do it is this one. That creates flow, and that creates a velocity gradient. But if I create a velocity gradient because of this effect here, I will tilt the molecules. So if I create a small perturbation like this, believe me on the sign, I will tilt the molecules more, and that's a mechanism to make it unstable. So I need two things. I need a gradient in the active stress, and I need the flow alignment parameters. And if both of these exist, there is an instability because I need a flow, and the flow increases the perturbation that creates the flow. So that's the basis of what's behind what I will tell you. Now, what I'm claiming is that there is a critical value of the thickness for this instability. There is a critical L above which the system flows, and the director is not homogeneous, it varies with space. So the system spontaneously flows. So I'm doing it to you exactly the way we did it historically, because when we got these equations, this is the first thing we did, and that was more than 10 years ago. So what I want to do now is take these equations and show you why, in more mathematical terms, there won't be more than what I said, but at least for people like me, it's nice to see equations. So I will show you equations. I'll tell you first in the beginning that I will cheat. I won't keep all these terms. I will only keep some of them because they lead to the effect, and I'll give it to you as an exercise. If you put all of them, the only difference will be numerical coefficients.
Here what you're doing is variable computation and putting finite size on the curators, I guess. So you're not taking into account what you were saying before about you have a boundary, so I have to
Oh, no, of course I will. I will put a boundary condition on the velocity here. And I will be extremely naive. Sorry, I didn't talk about that. I will assume that it's like a normal liquid, so there is no slip here. So V equals 0. And here the stress is 0. Sigma total. Now, I changed my notations because I wanted to have the same as in my notes. But contrary to what you do when you do hydrodynamics, I'm not allowed to exchange sigma xy and sigma yx. They are different because the stress is not symmetric. Okay, so let's do it. I need to keep these equations. So I'll call x this direction, y this one, and my system is invariant by translation along the x direction. So Vx only depends on y, and there is no Vy. Now the force balance equation becomes very simple. It's dy sigma yx. So sigma yx is the force in the x direction on the surface perpendicular to y, plus dx sigma xx equals 0. But sigma xx doesn't depend on x. So dy sigma yx is equal to 0. So sigma yx is constant. And because on the surface sigma yx is equal to 0, sigma yx is equal to 0 everywhere. So this is where I cheat. I announce it right away. So sigma yx has this term here. And I will not write numerical constants and things like this. So sigma yx is equal to eta And the only component that exists in here is dvx dy. So it's eta dy vx. I will ignore this term. You can put it back. It doesn't change qualitatively the result. And I want to write this one. So I want to write zeta delta mu qxy. P is cosine theta sine theta. If theta is small, cosine theta is 1, sine theta is theta. So this is minus zeta delta mu theta. Okay, so this is my first equation that expresses force balance. There is another term. I don't write it. It will only change numerical factors, and it's easier to see what happens with this one. Then I write this equation here. So I'll erase that. So I'll write it for Py. Py is theta, so it's dPy dt. I take, so theta, this is theta. Now, you can do the same thing with theta pi over 2, and the result is the same. You shouldn't do it for another angle, because it flows by itself, because there are gradients due to that. So, but if I do it for 0 and pi over 2, there's no problem. So dPy dt, but I look at a steady state. P is mostly like this. So h perpendicular is hy. So it's k d2 dy squared of theta. And then I have a term which is here, Py, and I have only Vyx, so I have to put Px, and Px is 1. So it's minus nu. And that's it. So these are my two equations. This one I don't need to write. This one I don't need to write because I don't care how much energy is going into the system. Using these three equations, you can also look at the energy balance in the system. What puts energy in the system is that, and what dissipates energy is these two terms here. So that's what I want to solve. I take dy Vx from here. So dy Vx is zeta delta mu theta, so k d2 square theta minus nu1 zeta delta mu theta over eta. And there's a gamma here. Gamma 1 is equal to 0. I'm going to check that I didn't forget anything. K over gamma minus nu1. Okay. Now I will divide to make it look like an equation I know. So I write d2 theta dy squared minus zeta delta mu So as I said, because what I want to show you afterwards works like this, I will assume that the system is contractile. Or zeta delta mu. Now, if zeta delta mu is smaller than 0, this whole coefficient here is positive, and then my equation is just d2 theta dy squared plus 1 over L0 squared times theta is equal to 0, where 1 over L0 squared is all that. And I'll let you check dimensionally this is a proper length. Now this is, I want to solve with two boundary conditions, one here and one here. So if y equals 0, theta equals 0, and if y equals L, theta equals L. Theta equals 0. Now the solution is theta equals theta 0 sine, because I want to impose this one, y over L0. I impose this condition, but then I cannot impose the other one. I cannot impose the other one except if y, so theta of L is equal to 0, if y so as long as L is smaller than LC, there is no way I can impose a boundary condition at y equals L, and the only solution to this problem is theta equals 0. Wait. Who wanted to ask? Right. My two equations are here. This one? It's this term here. Now I want sigma yx. So alpha is y and beta is x. So qyx is px py, okay? But px is cosine theta and py is sine theta. And if theta is small, this is theta. The second equation comes from here. H alpha is hy. I write the equation for y. But hy is h perpendicular because p is along x more or less. So this is this term here. And this one is here. I want py. So alpha is y, but the only component which is non-zero is vyx or vxy. So beta is x and px is 1 because it's cosine theta. Okay? So this is where this term comes from. And maybe, no, I didn't even forget it too. Okay? The numerical prefactors I don't want to write. I'm looking for a steady state solution, yes. Oh, because there is one which spontaneously flows. What you're saying is I could keep this term here and see how it evolves with time. That will be a little bit more messy, but it will converge to the steady state solution in the end. Oh, it's dynamically stable, no problem with that. And of course, I didn't say it, but instead of putting y over L0, I could put ny over L0, but the first instability will come for n equals 1. So I'm saying if L is smaller than LC, what this tells me is that there is no other solution than theta equals 0. If L is larger than LC, there is a solution which remains finite, and if L is close to LC, the solution is theta equals theta 0 sine pi y over LC. Now, of course, I need to calculate theta 0. I cannot do it from the linear theory, so if I want to calculate theta 0, I have to go back here and expand in powers of theta. There is a term in theta cube that comes out, and from the term in theta cube, you will write that it's sine y plus sine 3y, and you will calculate theta naught. So only if L is larger than LC, I can calculate theta naught. So what I'm telling you is that if I have a thin film on a surface, if I increase the thickness of the film, if the film is very thin, there's no flow and the orientation remains parallel to the substrate. If I increase the thickness of the film, I reach a point where theta is no longer homogeneous. It varies with y. And because of the argument I gave you, and because of this equation here, if theta varies with y, I can calculate the velocity gradient. You will agree with me, and I erase my drawing, but I can make it back. There is no slip here, so the velocity is 0 here. This term, the velocity gradient doesn't change sign, and so the liquid flows. Now, of course, there is a spontaneous symmetry breaking. I have the same probability to flow to the right or to flow to the left, and both solutions are acceptable. So this is what I call the Frederick's transition. This is a very fundamental instabilities of active system. Essentially, what it tells you is that if you take an active system like this, where one of the length scales is larger than this critical length, the system spontaneously flows, and there is no steady state at 0 velocity. And that's true essentially in all cases. So there is a critical length, which is this LC, which is here, that when the system is larger than this critical length, it becomes unstable to flow. Now, I insist on the fact that I cheated. I ignored some of the terms, and I ignored them not because they are negligible. They have more or less the same contribution as the one I said, but this exactly does what I told you qualitatively. I create the flow because I have a gradient in orientation, and if there is a flow, it changes the orientation. Now, what I will do is give you the right answer. If you do it correctly, meaning correctly, you have to put the anti-symmetric stress, which I ignored. You have to put back this term, and that's it. So there are two terms which I ignored. If you do that, you find the same qualitative result with a critical thickness, which is here, 1 over LC squared equals 2 So here is the correct critical length that takes into account all terms. You can see the one I ignored this one, for instance. This one comes from the convected derivatives here. There is a v dot grad term. This one is higher order, but the rotational term omega cross p contributes here. So that's where the one is coming from. If I start from something which is homogeneous, at smaller than LC, it's perfectly stable. No, it's dynamically stable if L is smaller than LC, and if L is larger than LC, it's dynamically unstable. Okay. So then there is a second transition corresponding to mode n equals 2, and then you increase. If you make it larger and larger for an infinite system, eventually the system might become chaotic and things like this. There is a beautiful poster by Ricard that shows you that. He made great simulations on that. No? I say they are great. You're not allowed to say it. But yes, we see something that people have called active turbulence or whatever. We could argue whether this is turbulence or not, but if you go to very large system, it becomes chaotic. Uh, the first thing that was done on that were numerical simulations, if I remember well, in the group of Julia, where they observed this transition, and it corresponded well to this kind of theories. And for 10 years, there was no experiment at all. What I want to show you afterwards is experiments on these systems and show you that with tissues, we can observe directly this transition with slightly different boundary conditions. I can change the boundary conditions as I want. You can say it slips here, you can say it slips here, you can put a second wall here. There's always a transition. This one is the most spectacular because there's a flux of liquid. Without pushing the liquid, you create a flux of liquid. So that's my first example. The other thing I want to tell you about, but I'll do it fast because I guess many people talked about that, is defects in these active pneumatics. Mais c'est bien, hein? So if I relax the Onsager symmetry relations, I'm allowed to put something different here. I'm allowed to put something different here, but this one I didn't apply, and this is the only thing that changes. The value would change, but nothing bad will happen in the sense that the transition will survive. Except that if I relax the Onsager conditions, it means that the system is nonlinear, and then I should have to write all the nonlinear terms here, and there's a whole bunch. So, and it doesn't make sense to do that. I mean, if you have a physical argument on which linear term is important, you should write it. But if not, you will have dozens of terms which are completely irrelevant. At least this is my feeling. Any other? These are the young people, Julien and even Gerhard, who is about my age. Why do you get no flow? Because if the system is very thin, the viscous stress is very high. The viscosity, it goes like 1 over the thickness, essentially. So that's what happens if you go beyond. I agree. Yes. Who showed that? Francesca Guest. Yes, and that corresponds well to this. I agree. This is the second example. It's also last year. So it's not more recent than the one I want to show you. Yes? Somebody really young. So yes, that's a nice comment. So there is an instability for films in extensile system. The mechanism of instability is different, and this was studied by Sriram Ramaswamy and one of his students, Sumitra. Yeah, I think she's right. Okay. No other question? Parfait. Yeah, there's a comment I can make on what you said. There's an experiment by Dojik where he's looking at microtubules in a ring like this, and he sees flows. I don't believe that this has anything to do with this mechanism. He's below the pneumatic transition in his experiment. And here I said from the beginning that I want to be way in the pneumatic phase. So this first experiment, which is very nice, and when I see spontaneous flow, there is no doubt, but it doesn't have anything to do with that for me. And then it drives the... Okay, so defects in active pneumatics, and I will be very brief. So as you heard from Francesca Guest, there are topological defects in pneumatics. And I will discuss them only in 2 dimensions because the tissues I want to show you are in 2 dimensions. Now, if you look at a pneumatic system, and I want to insist on that, the defect can have a half-integer charge, topological charge, or an integer topological charge. So the simplest ones are +1/2 and -1/2 defects. So the defect is here, and the orientation is something like this. And there is a singular point here where the orientation is not well defined. This one is a +1/2 defect. What it means is that if you start from this point, you make one turn, so you turn 2 pi in space. If you look at the orientation of the pneumatic, it turns by +pi. And the topological charge is a ratio between these 2 numbers. Change in the angle of the director, which is pi, divided by the angle that you turn, which is 2 pi. So this one has a charge S equals 1/2. And then there is a defect with a charge -1/2. Maybe the point I want to insist on is that these defects exist for pneumatic. They don't exist for polar systems, because if I try to put an arrow, for instance, suppose I put an arrow here, and I follow my arrow, and here on this line there is a jump between this orientation and this one, so this defect doesn't exist for polar order. This one is the same. So this one has S equals -1/2. If you turn from this line by 2 pi, the orientation turns by -pi. So the charge of the defect is -1/2. And if you draw arrows, so you will draw arrows like this. On this one, if you want to be continuous, you have to draw it like this. Here like this. And then on this line, there is a jump. So this defect doesn't exist for polar order. Now, if you take the next defects, it's +1 and -1 defects. So the +1 defect can be something where the molecules, the center of the defect is here. The molecules do that. So they are radially oriented. If I turn by 2 pi, the orientation obviously turns by 2 pi. This one, people call it an aster. An alternative +1 defect is something where you turn around the defect. Again, if you turn by 2 pi, the orientation, which is pi over 2 here, will turn by 2 pi. Now there's one which is less known, which is a spiral plus one defect, which is intermediate between these two. So it's something where the molecules go in spirals like this. So these are three forms of the plus one defect. The minus one defect only has one, like this. And if you put arrows on any of these, I can put arrows like this. It works, so these defects you observe also in polar systems. Now, if you have an equilibrium pneumatic, the energy of the defect is proportional to the square of the charge, proportional to K, the stiffness of the pneumatic, the square of the charge, the log of the size of the system divided by the size of the core of the defect plus a constant. Which means that the one with lowest energy are the one with lowest charges. So essentially, in pneumatic systems, you observe that. If your system is polar, you will observe things like this. The other thing, yes? Oh, L is the size of the system, and RC is the size of the core. So the size of this region here, where the order is not well defined. Okay? Now, because defects with higher charges have a much higher energy, you observe the ones with low energy. And in passive pneumatics, you observe plus 1/2 and minus 1/2 defects. Now, defects interact. They interact like charges in 2 dimensions. So the interaction between 2 defects W of R is minus K S1 S2 log of R, and there's a constant which is pi or something like this. Now, which means that defects with the same charge will repel, and defects with opposite charge attract. Now, this tells you that a plus 1/2 and a minus 1/2 defects will attract, and if they come too close, they can annihilate, and then you have to conserve the topological charge, and by continuous deformation, you can eliminate a plus 1/2, minus 1/2 defects. So if you have a system with many plus 1/2 and minus 1/2 defects, they will attract with opposite charges, and you will eliminate pairs of defects. Static systems. So that's a question I wanted to ask you. For instance, in your opinion, what happens to this defect or this defect if there is activity? doesn't. Yes, there's no critical. They have to move because they have a gradient of the order. Yes. So how do they move? Yes, I agree. So how do you think this one moves, for instance? What should it do? Yeah, it should rotate, and it should rotate with equal likelihood in the positive and negative direction. This one is the same. The spiral should also rotate. And this one, nothing happens because it's radial. Now you can take the equations that I showed you. With this equation, this one doesn't rotate. The velocity that you will find is exactly 0, which is an artifact of the linear theory. The philosophy is that anything that can happen should happen, and the active theory should tell you that this one rotates either in the positive or negative direction. If you take the most obvious nonlinear term, it starts to rotate. The spirals do rotate. Okay. -1 defects, what happens to it? There is no preferred direction, so it cannot rotate. All the orientations of the defects are equivalent, and there is no force that rotates it. Now, these two, you heard about it. What happens to this one? It moves. So there is so these ones rotate. This one has a translation. This one? No, because there is no preferred direction. So +1/2 defects move. +1 defects can rotate. But the -1/2 doesn't move. It moves because there are fluctuations, and then it diffuses. And the -1, the same thing, will move because there are fluctuations, and it diffuses. Now, if you take the equations that I gave you, you can try to study the rotation velocity of these defects, and you can try to study the translation velocity of these defects. Now, in the following, and my argument will be defects, I will only study pneumatic tissues. In pneumatic tissues, the defects which are observed, only this one and this one. So the prediction is the +1/2 defect should move, and the -1/2 defect should be static or diffuse. And there should be attractions between +1/2 and -1/2 defects. Okay? Yes. No, but topologically you have to evacuate them from the surface. If they move to the surface, they can be eliminated. But there is no way you can, if you have a single defect, whichever it is, there is no way you can eliminate them except sending them to the surfaces. Because of topological reason, this has nothing to do with energy. Except that the one that moves might go spontaneously to the surface. One by one. Pairs of defects can annihilate. +1/2 and -1/2 defects can annihilate, and then they disappear, and the number of pairs of defects can diminish with time. Well, if you have a single defect, what you say is true. Oui? Well, so, in which condition? So, I'll show you experiments, maybe not today, but tomorrow I'll show you experiments, and you will see it just diffuses around. Another thing that I need to tell you is how does it move? So it moves in different direction. Okay, in the P equation, you need to add a P dot grad P, which is the term that we discussed several times. This one makes this vortex defects rotate. And this one rotates whatever you do. So the other thing you need to know, and you will figure it out if you do the calculation for that, is that if the system is contractile, which is a system that I will consider, it moves like this. So it moves in this direction with respect to the defect if the system is contractile. It moves in the opposite direction if the system is extensile. further question? Julia, you want to add something on defects? No, you could talk for hours on that. But I have enough for what I want to show.
Just one question. So the ordering field, when it's evolving, it can also impact the density field. Is it clear that if you have a stem that's not incompressible in the middle of defects,
You mean,
voids or
could I create voids at this point? Or you could, I guess. I mean, there are couplings between the density and the order parameter, that's for sure. I will miss them the way I did it because I assume that my system is incompressible. But yes, of course.
You have a splitting of an integer defect into two half integers.
In pneumatics, yes. You can split. In active system, as far as I know, they never observe the +1 defects. You have? So Julia sees that.
About -1.
What about this one? I can't answer. So there is a way, if you take 2 + 1/2 in opposite direction, you can generate a +1/2 defects. And if you take this law here, you will see that for pneumatics, what Ramin says is true, and the +1 defect should split into 2 + 1/2 defects. The energy is lower. That's true. What should I do? Let me just start what I want to say and talk 5 more minutes. Okay, so what I want to do now is go back to tissues. Now the first point is that there are tissues where the cells are not roughly spherical but are very strongly elongated. Now in these tissues, the cells are what I call confluent. They touch each other and they fill space. And there is orientational order. Now this orientational order can be polar or it can be pneumatic. Now if the order is polar, symmetry arguments tells you that the cell should all move in the same direction. Now these are called mesenchymal tissues, and in this case, associated to the polarity, the cell have a spontaneous velocity. The point I want to make is that I can tell apart polar from pneumatic tissues just by looking at the defects. As I told you, if I have only +1/2 and -1/2 defects, or if I see any +1/2 or -1/2 defects, the order is pneumatic. In a polar tissue, the only thing that I should be able to observe is +1 or -1 defects. So this is how I will tell them apart. In polar cells, yes, I mean, how should I say that? Inside cell, for instance, in keratocyte cells, you see swirls where the actin filaments are rotating. which is not with cells, but that's, I don't have any precise, but this is what should be observed if there are ones. Probably if you force the geometry and put them into circles and things like this, you can obtain defects. I cannot quote any specific experiments on that. I will stop here. What I want to show you next is that if you look at a tissue which has pneumatic order, it has to be active. So my next point is that tissues with pneumatic order will be active. And I'll show you why tomorrow morning. And I'll stop here. Voilà. Further questions? You want to cut it here? This one you want to cut, and what do you want to put on the other side? Parallel line.